24 hours ago, a piece of abandoned SpaceX hardware hit the moon at 5,400 miles per hour. What we told you was coming has happened. The crater exists. It is on the lunar surface right now, permanent, measurable, the first human-made impact crater on the near side of the moon ever confirmed with advanced knowledge of its creation. And we already have the first images. Not from NASA, not from a billion-dollar space telescope, from South Korea. The Korea Aerospace Research Institute's Danuri lunar orbiter, a spacecraft the size of a washing machine, orbiting 340 to 350 kilometers above the moon since December 2022, executed 8 separate imaging passes over the impact site before and after the collision. It captured the moment of the aftermath. It documented the dark scar left on the gray lunar surface. And it released those images this morning, less than 24 hours after the impact. What those images show, what they confirm, what they still cannot tell us, and what arrives next from NASA's Lunar Reconnaissance Orbiter, that is what this video is about. But first, what Danuri risked to get these images, because that part of the story has not been covered anywhere. New here, this channel covers what is actually happening in space right now with real numbers and real stakes. Subscribe. You will not want to miss what comes next. Danuri launched from Cape Canaveral on August 4th, 2022 on a SpaceX Falcon 9 rocket. The irony of that detail is not lost on anyone following this story. The spacecraft that photographed the crash site of a Falcon 9 upper stage was itself launched by a Falcon 9 4 years earlier. It carries 6 scientific instruments, including a high-resolution camera called LUTI and a wide-field polarimetric camera called PolCam, which measures how light reflects and polarizes off the lunar surface at different angles. When trajectory predictions for 2025-010D were published in the weeks before impact, the Korea Aerospace Research Institute did something that has received almost no attention in the coverage. Their engineers ran the orbital calculations not just for the incoming stage, but for their own spacecraft. They needed to know whether Danuri itself was at risk. The uncertainty in the predicted impact trajectory of the incoming stage was large enough that a close conjunction with Danuri could not be ruled out. Engineers considered the possibility that the spacecraft could be hit by ejecta from the impact, or that the impactor itself could come dangerously close to the orbiter in its final approach. In mid-July, the KARI team made a deliberate orbital maneuver, originally planned to prepare Danuri for an upcoming near-total lunar eclipse on August 28th. That maneuver, Kim Yoon-yuk of KARI explained in a post-impact statement, brought a slight change in the phase of the spacecraft's orbit. The change cancelled what would otherwise have been a potentially dangerous conjunction between Danuri and the incoming stage. The spacecraft that photographed the crater survived because of an orbital adjustment made 3 weeks in advance for a completely different reason. Space operations run on margins that most coverage never reaches. The fact that Danuri was in position to capture 8 imaging passes of the impact site is not incidental good fortune. It is the result of careful trajectory management by a team that understood what was at risk and planned accordingly. Here is what the images actually show and what they do not. The Danuri LUTI high-resolution camera captured the impact site at a distance of 340 to 350 kilometers. At that distance, the instrument can resolve features smaller than 5 meters across. What the images show, released publicly by KARI via their official channels on August 6th, is a dark mark where no dark mark existed before. A region of altered terrain, noticeably different in reflectivity from the surrounding gray lunar surface, spreading outward from the impact point near Einstein Crater on the moon's western limb. The Korea Aerospace Administration was specific about what has been confirmed. Changes in terrain around the impact site and traces of ejecta spread. The terrain is darker. The surrounding surface shows the fingerprints of material thrown outward from the impact and deposited across the nearby ground. What the Danuri images cannot yet confirm is the precise size and shape of the crater itself. The orbital geometry of Danuri's passes, combined with the lighting conditions at the impact site and the resolution limits of the instrument at that distance, means the before and after comparison shows the impact's effect on the surface, but does not yet resolve the crater's exact dimension. That measurement requires the LRO a different instrument with a different orbit and a significantly higher resolution narrow-angle camera capable of resolving features down to half a meter. The LRO was on the opposite side of the moon at the moment of impact and could not photograph the immediate aftermath. It is scheduled to pass over the impact region on approximately August 11th, 6 days from now. What it finds when it looks at that patch of lunar surface will answer the questions the Danuri images have raised. But before the LRO images, something happened from the ground that nobody predicted. At the Instituto de Astrofísica de Andalucía in Granada, Spain, a team of astronomers had positioned their instruments on the moon's western limb in the hour before impact. José María Mariedo, a researcher with dual doctorates in astrophysics and chemistry, had his team's telescope trained on exactly the right patch of sky at exactly the right time. What they captured was not the impact itself. The flash lasts less than 1 second and is too brief for most imaging systems to reliably record. What they captured was the aftermath, a preliminary video showing the evolution of ejected material rising above the lunar limb and spreading outward from the impact point, visible against the black sky above the moon's edge. This is the first ground-based video evidence of the impact's ejecta plume. It confirms that the plume was real, that it rose above the lunar horizon as predicted, and that it was visible to sufficiently sensitive instruments positioned in the right location. The video will be used alongside Danuri's data and the forthcoming LRO images to build the most complete picture ever assembled of a known impactor lunar collision. 3 independent observation systems, 1 Korean spacecraft in lunar orbit, 1 Spanish observatory on the ground in Andalucía, 1 NASA orbiter arriving in 6 days, each one capturing a different part of the same event from a different vantage point. This is what planned observation of an unplanned impact looks like. Here is what the combined dataset already tells us before LRO has even looked. The impact occurred at 6:34 to 6:35 UTC on August 5th, right in line with predictions. Bill Gray's trajectory calculation, built from over 1,000 telescope observations accumulated across 19 months, was accurate to within minutes and to within the observation radius that allowed Danuri to plan its passes. The dark mark, visible in the Danuri images, is consistent with the predicted crater size of up to 27 meters, approximately the length of a basketball court. A fresh impact crater on the moon is darker than the surrounding terrain because the impact excavates subsurface material that has not been exposed to solar radiation and the space environment for billions of years. That unweathered material, called immature regolith, is darker and less reflective than the mature surface it sits beneath. The darker mark visible in Danuri's images is exactly what fresh excavation looks like. The ejecta traces spreading outward from the impact point are also visible in Danuri's data. The Korea Aerospace Administration specifically confirmed traces of ejecta spread material thrown from the crater and deposited on the surrounding surface. That pattern, when fully mapped by LRO, will tell researchers the lateral extent of the ejecta curtain and whether it matched the predicted spread of approximately 183 kilometers in every direction. The polarimetric data from Danuri's PolCam instrument adds another layer. By measuring how light reflects off the lunar surface at different angles before and after the impact, researchers can characterize changes in the physical properties of the surface material, particle size, compaction, structure that are invisible in a standard photograph. This kind of measurement has never been taken of a fresh impact site within hours of formation. It is new data about how impact physics alters the lunar surface at the smallest observable scale. But here is what none of these images can yet tell us, and what that missing information means. The crater visible in the Danuri images is, at this stage, unresolved in terms of its precise morphology. The question that matters most for the science of hollow impactors, does the Falcon 9 upper stage produce a single crater or a double crater, cannot yet be answered. This is the critical question Bill Gray has been most interested in throughout this entire story. When the Chinese Chang 5T 1 rocket stage hit the moon's far side in 2022, it produced a double crater, 2 overlapping balls that implied 2 separate mass concentrations along the length of the object. That double crater revealed something China had never disclosed about its mission. The Falcon 9 upper stage is a different object. Its mass distribution is fully documented. The engine at the base is the heaviest component. The empty propellant tank above it is essentially an aluminium shell around empty space. Gray's expectation, based on that documented mass distribution, is a single crater because the stage did not carry an undisclosed additional mass at its far end the way the Chinese stage apparently did. If LRO images show a single crater of approximately 27 meters width, Gray's model of hollow impactor behavior is validated. The Falcon 9 behaved as its specifications predicted. If LRO images show something unexpected, a double crater, an asymmetric ejecta pattern, a crater significantly larger or smaller than predicted, the models require revision. That revision matters beyond academic interest. As more commercial missions launch hardware onto translunar trajectories in the coming decade, the ability to predict what each piece of debris will do when it eventually hits the moon determines whether future Artemis infrastructure can be placed with confidence or uncertainty. The LRO answer arrives on approximately August 11th. This channel will cover it when it does. There is one more dimension to what happened this morning that the image coverage has largely missed. The Danuri images released today are the first ever captured of a lunar impact site within hours of formation from a known artificial impactor. Every previous lunar impact crater in the archive, from natural meteoroid strikes to the deliberate Apollo-era SIVB crashes, was photographed days, weeks, or years after the fact, if it was photographed from a purpose-positioned spacecraft at all. What Danuri captured this morning is a time series, 8 imaging passes, beginning 30 minutes before impact and continuing through the following hours of a surface that was undisturbed lunar terrain before 6:34 UTC and an active impact site immediately afterward. That time series, showing the surface state before the immediate aftermath and the evolving changes in reflectivity and polarimetric properties as the freshly excavated material settled, is scientifically unprecedented. The Korea Aerospace Administration Administrator Oh Tae-sok said in a statement that the achievement will provide an important foundation for expanding the country's lunar research and future space exploration strategy. That is the language of institutional restraint. What he is describing is the first operational demonstration that a lunar orbiter with a known position and flexible orbital control can be repositioned to observe an unplanned impact event within hours of advance notice and can capture scientifically valuable data before any other spacecraft in the cislunar environment. That capability matters for what comes next in lunar exploration. Not just for this crater, for every crater. For every impact event, natural or artificial, that strikes the moon while human infrastructure is present on its surface. Danuri just proved that it is possible to observe these events in near real time from orbit, with instruments sensitive enough to measure surface property changes within hours of formation. Here is where everything stands right now. The crater is confirmed. The dark mark is on the surface. The ejecta spread is documented. The ground-based plume video from Spain is captured. Danuri's polarimetric data is in processing. LRO passes over the site on approximately August 11th. When LRO releases its high-resolution before and after comparison, the image that will answer the single crater versus double crater question and measure the crater's exact dimensions, this channel will cover it immediately. That comparison is the final scientific payoff of everything that has happened since Bill Gray ran his orbital solution in September 2025, predicted an impact that nobody else was watching for, and published the result on a personal website in New Hampshire without ceremony. One astronomer. 1,080 days from launch to confirmed crater. The first complete scientific dataset of a known impactor lunar strike in history. Subscribe. The LRO images are coming next week.